All right, good afternoon. Welcome to the second speed session. And I guess, yeah, we'll keep out 8 minutes. If we have a little bit of time to finish early, we maybe can ask a few questions, but if you want, you can also hold questions at the end for all the speakers. I think we have 7, if I counted correctly. It might be 8, I don't know, somewhere in there. Somewhere between 6 and 10. So, but first off, we have Daniel Timme from Florida State University, also a captain in the Air Force, right? Major now, major in the Air Force. So, all right, Daniel, go ahead.
I have a timer right here too, so I don't hold on. Right, sir. All right, so good afternoon, everyone. My name is Daniel Timme. Today I'll be talking about a Bayesian approach we came up with for non-parametric multivariate process monitoring, where we use universal residuals. This is not liking me now.
It might be we have to do the first slide manually and then. All right, let me find where I'm at here.
This doesn't count against me, right?
Yeah.
I'll pause it for you.
Okay. Now let's try the thing now.
Should have tried it before I started talking.
Okay.
It's on me. I apologize.
That's fine. It auto use the computer for the first one and then it works.
Okay. Well, good afternoon. My name is Daniel Timme. I'm talking about a Bayesian approach we came up with for non-parametric multivariate process monitoring. We use universal residuals. So a profile is a noise-induced functional relationship where Y is a vector of responses, X is a d-dimensional matrix of predictors, and epsilon is a noise vector. And we're going to be using this in a change point methodology where we're going to be testing this hypothesis here, where capital T is the run length and tau is the last in control time step. And in control means that we're operating only in the presence of natural variation or background noise, and we're going to represent that with a function f. Out of control, we're going to have variation beyond that natural variation, and we're going to represent that with a function h. Now we're going to assume that a practitioner has a set of m historic profiles that are known to be in control. We're going to be working with a linear and nonlinear in control function, a localized change out of control function, non-parametric method for modeling, and multivariate predictors. And what we're hoping to achieve is a method which is computationally fast, has a low false alarm rate, even for large values of tau, and has fast detection or a low average run length. Now, there's actually 2 types of average run length. There's an in control average run length and an out of control average run length. And they're exactly as they sound. They are just an average. So for the in-control run length, we consider the toy example up top where X marks a change point. We see that we have change points at time t equals 5, 4, 2, 3, and 6. And if you take the average of those, you're going to have an ARL naught of 4. Now, in literature, we're generally concerned with an ARL naught of 200 and finding a control limit which is associated with that. And I will hit on that a little bit more. For the phase 2 analysis, the performance metrics we're considering are an out-of-control average run length and a false alarm rate. Now, the out-of-control run length is the same as the in-control run length, except now we're considering that value of tau, because recall that is the last in-control time step. False alarm rate is defined as the number of system restarts divided by the system starts plus restarts. Now, when we have a false alarm, we restart our system process monitoring. So the number of false alarms is the number of restarts. So it's simply the number of false alarms divided by the sum of total starts. To consider the toy example down below, for the out-of-control average run length, we are only concerned with time greater than tau because that is the last in-control time step. And you see that for trials 1 through 4, we have a change point detected at t equals tau plus 1, and trial 5 at t equals tau plus 2. So if you subtract out that value of tau, last in-control time step, take the average, you have an average out-of-control average run length of 1.2. False alarm rate, we're only concerned with the time that is less than or equal to tau. So you see at trial 2 and trial 4, we have false alarms. So there's total 2 false alarms, 5 trials. So 2 divided by 5 plus 7, approximately 0.2857 for the false alarm rate. Now, universal residual, to put it quite simply, it's a transformation of the residuals from whatever distribution they're in into the uniform distribution. We're going to be doing 2 things with this. One, we're going to be using with that set of historic profiles to basically create an empirical CDF. And 2, when we start our online process monitoring, what we're going, there we go. When we start our online process monitoring, whenever we get a set of residuals, we're going to use them with the CDF. And the plot bottom stage right If they come out looking uniform, we say it is in control. If they have something that's not uniform, such as bottom stage left, then we say it is out of control. And we're going to do this with a Bayesian hypothesis, inference on the hypotheses, where we're going to be using the multinomial and Dirichlet multinomial distributions. Now, at every time step, we're going to have T+1 hypotheses, and that allows us to look into the future and say we're still in control, and assess previous times and say that if we misidentified as being in control, we are actually out of control. So the hypothesis when tau is greater than t is simply a product of the multinomial distributions. Hypothesis for tau equals 0 is a product of the Dirichlet multinomial distributions, and anything in between that is going to be a product of the multinomial times a product of the Dirichlet multinomial. Once we have all the prior distributions, we'll be able to get the posterior distributions for the T+1 hypotheses. So the first thing we're going to do is not hit the laser pointer. With the set of n-historic profiles that we have from the practitioner, we're going to fit regression trees to that. And we're going to create a set of integers from 1 to m, which we're going to call script A. And then in a loop from I equals 1 to m, we're going to have a set B where we just remove that value I. We're going to find m-1 predictions using the response from I at all the trees in set B. We're going to calculate the mean of those predictions and then get the residuals. Once we complete this loop, we will have m vectors of residuals, which we will stack. We will use kernel density estimation on that to obtain a CDF, which we're going to call Z. During the phase 2 simulations, we are going to sample our predictors from the uniform distribution with values between 0 and 1 for d equals 3 dimensions. The noise from the normal distribution between with a mean of 0 and a variance of 1. Call again tau is that last in control time step. So if t is less than or equal to tau, we're going to use that in control function f. If t is greater than tau, we're going to use the out of control function h. Just as before, current response, all previous regression trees get a bunch of predictions, find the mean of those predictions, calculate the residuals, and then we can use that with the CDF we got from the historical profiles and get the universal residuals. We're then going to bin those universal residuals, sample from the multinomial and the Dirichlet multinomial, calculate all the prior hypotheses, and then we'll be able to calculate the posterior probabilities for the T+1 hypotheses. Now we're going to do this for control limits of 0.5 and a lower control limit, which comes from that ARL not 200 that I mentioned earlier. And we are going to compare these to other methods. 2 of them are ours, where we use regression trees and random forest with Kolmogorov-Smirnov, and a single index model, which was presented from Maguchi et al. And we're going to use the performance metrics of the out of control average run length and the false alarm rate that I mentioned earlier. And what we see is with the average run length, the out of control average run length, we outperform the other methods, whether we use 0.5 or a low control limit in every single scenario. However, for the false alarm rate, we find that we only outperform all the other methods when we use the 0.5 control limit. When we use the lower control limit that we get from the ARL not of 200, we don't outperform our previous method at all for false alarm rate, and we only outperform the single index model in 3 out of 4 of the scenarios. Now, in literature, we are generally doing this for tau equals 0.30, which you may have saw when I sped through those slides. We wanted to test it for larger values of tau, 100, 500, and 1,000, and we found that we are still able to achieve a very small out of control average run length and false alarm rate. We also found that this method is much faster than our previous methods, as well as it's also very versatile because you can use anything you'd like to model, as long as you can get predictions. The average run length, again, just to summarize, is much lower than all the other methods with both control limits, and our false alarm rate we were able to only outperform when we had a control limit of 0.5. I do not believe I have any time for questions, but I would love to see all of you at my poster.